you can read my bio in the app. I'll give you the short version. I've been using AI for about 10 years now, but I've been in the internet world and high-performance computing world since the mid-1980s. And the last 2 years, almost everything I'm doing is related to AI in some form or another, not just using it, but actually developing AI capabilities for scientists, which is different than the general chat GPT sorts of stuff. And so what I want to do today is give you a grounding in AI without making you rack your brain for what you learned in high school in mathematics. And so I want to make it very practical. If I say something that is, you just don't get the buzzword or something like that, please just, wave your hand or go like this, and I'll know that I need to back up a little bit. All the slides that I'll use will have this footnote down, or most of them, the footnote down at the bottom here. And that will take you, that QR code right there will take you to the Google Doc, where you can find those references and even look them up. Most of them have links to them, so you can look at the source material for the talk. I don't know if I would recommend doing it while the talk is going, but if you feel the need for a mental distraction, then go for it. I won't be offended. So that's the complete bibliography. And as I said last year, if you're interested in using any of these materials when you're back home, I'm very happy to give them to you, and so you can download them. And if it's helpful, you want to give a talk to your youth group or something like that, you can always have me zoom into your youth group if you want, but if you want to use these slides, I'd be happy to kind of give you a script and talk you through by Zoom or something like that. So think of this as like you're meeting Charlie, but I'd be your AI go-to guy throughout the year. Obviously, don't call me every morning or anything like that, but I'm pretty responsive to email. So throughout the afternoon, I want to kind of cover 4 big topic areas. So the first one is just, decoding the terms like machine learning and AI model and deep learning and generative AI and that sort of thing, and help you kind of tie them to everyday life. And then I want to talk in 2 different sections about opportunities for us to use AI, some of the things that AI is really good at, and some of the things that AI is not so good at. And then we'll close out with a discussion about what these new changes and new capabilities of artificial intelligence kind of mean for us on the street, in our churches, in our homes, and what are some of the things that we should be cautious about moving forward, and what is the government doing about it, and is this really going to wipe out humanity? I'll just spoiler alert, no. But it's worth just kind of thinking through these things. So let's start with these foundations. So first of all, AI, artificial intelligence, is a term that was coined in the 1950s. I'm giving you sort of a background here, technology-wise, of some of the key innovators over the last century or two, whose work we build on with computing and AI. I found this picture from what used to be called the National Aerodynamics Council or something like that, what became NASA. Back in the 1940s, a computer was a human that sat at a desk and did calculations. And so, we're maybe kind of coming full circle with people talking about, is an AI as smart as a human? While those computers right there in that picture are way smarter than any AI, those people. Also, I was really excited last year because one of our computing heroes is John von Neumann, who's Hungarian. And there was a supercomputer center named after him at Princeton, and a friend of mine, has his desk chair in the lobby of his department. So he's like a hero in computing, and I got to meet his great-grandson, who was here last year. So von Neumann's line is, at least in that particular part of it, has embraced the gospel. That's really cool. Up at the top, you see 3 gentlemen who won what's called the Turing Award, which is the computer science equivalent to the Nobel Prize, a couple of years ago, and they won it because of their work in deep learning. So we'll talk about AI changed dramatically in the last 10 years, and why. It changed even more dramatically in the last 2 years, and why, what was it that spurred that change, and what's going to happen next if we could try to look down the road. So in 1950, Turing, who that Turing Award is named after, Alan Turing, he's probably best known. There's been at least one movie called The Imitation Game recently, but he's probably best known as the person who built this device to crack the German Enigma cipher machine. So the way they encrypted their messages, they had this machine. And what you might not know, maybe you knew that, you might not know, is that Turing based his design on something that the Polish mathematicians had done, so here in Poland. So he was able to build on the work of Polish mathematicians to break the Enigma code. Anyway, he proposed this, what he called the imitation game, or maybe what we've called it since then, which is to just kind of a thought experiment about like the title says, intelligence and computing machines. Could machines think? And the test that he proposed was that you have a screen with a person on the other side and a computer, and you're typing, not being able to see through that screen. You're typing back and forth, and can the computer fool you into thinking that it's the human for at least 5 minutes? And he, in the 1950, when he wrote this, he thought that we'd be able to do this within 50 years. And so he was a little bit off, but not too far off. We started to really see these capabilities. We could talk to the best, what's called natural language processors. The best ones 10 years ago you could talk to or type with for quite a while before you figured out that it was an AI. So over the years, one of the ways that and this is really an even bigger issue today, is how do you measure the intelligence or the capability of a piece of software? And early on, it was really, the work was done in the context of board games, because board games are very cut and dried, black and white. You can move a rook a certain way, and if someone else's chess piece can move that way and take the rook, there's no argument about it. There's no, I don't know, is there a tie? Is it possible to have a tie in chess? Maybe there is, but it's a tie. It's not like, we're close to being a tie, or I almost, I sort of almost beat. I can't take, so that's a picture of me. I won't take any credit for the AI part of this, but I was responsible for that supercomputer that I'm leaning against, and I let the MIT team use that computer for an entire weekend to play on this chess tournament, and I got quite a bit of flack from the other scientists who said that they were real scientists, not game players. The chemists and the physicists and the environmental scientists, because they didn't really view this as computer science. And in fact, now you would look back and say, absolutely, that's computer science. It's just that we're using a game to measure the progress in that software. So artificial intelligence, over its period of the 70 years that it's been sort of around as a field of study, includes lots of these things on the left-hand side, from speech recognition to image recognition, expert systems, et cetera. And then you could see these kind of major areas. And up until about 2012, machine learning was just one of those branches. And since 2012, machine learning has become the method that almost all of these other branches of AI use. So machine learning went from being like, one of our siblings to the person in charge of, I guess it would be sort of like Joseph, became like the lead brother. So, and then, here's a definition. Arthur Samuel is the guy that in the previous slide was playing checkers on television from IBM. And so he talks about machine learning as being associated with a computer or a piece of software being able to learn. Now, you also, it's maybe more clear now than it has been ever in the past, that machine learning models are all over the place. I bumped into somebody, a friend of my mother's, who said, oh yeah, they're foisting AI on us. And I said, well, they've been foisting AI on you for about a decade. You just didn't notice it. But it's, these algorithms are everywhere, from on your phone, that box that's drawn around. So that on my phone is a special application that will pick out extremely cute kids. They happen to be my grandkids. But if you hold it up, the box goes around the person's face because it's got an algorithm or a machine learning, an AI model running inside your phone that is looking for faces. And that's not sending an image back to, Apple headquarters or Google. It's actually running inside your phone. And, there's this watch app that I have that I could speak into, and it would be a model that's would be running on the iPhone connected to this. But we're going to talk a little bit about this as well and how AI plays a role in those things. At the heart of AI, currently, it wasn't this way 70 years ago, but the way that all AI, or 99% of AI, is done today is through artificial neural networks. We have a biological neural network here, and that is we have neurons and they're connected. So we have about 90 billion neurons in our brain, and about 1 trillion connections because they're all connected to multiple other neurons. And so we can write a piece of software that simulates a neuron, and that neuron can be turned on or off based on input from other neurons. And so you can see that we translate this idea of a neural network into software, and then over time, those networks get larger and larger and become more and more capable. So inside those little neurons are little decision processes that say, do I light up or do I not, based on all the things that are coming in from the other nodes. How many people have heard the term deep learning? And how is it different from machine learning is not really clear. Machine learning has been around for a much longer time than deep learning, and it refers to a network that's fairly simple. I'll just say relatively simple, not simple, but relatively simple. And machine learning models, I'll show you an example of in a minute. All the way back in the 1980s, the US Postal Service was using a machine learning model, if you will, to recognize handwriting so that they could automatically process the zip code on a piece of mail and sort mail. And the requirement to have a machine learning model work is that you have to carefully prepare data to train the model. I'll talk about what I mean by train in a moment, but you have to carefully prepare the data to train that model. And if you, on the upper left there, you might recognize that if you squint, this CAPTCHA, sometimes prove you're human, and so which one of these pictures has a fire hydrant or which one has stairs. You're helping to label images for this kind of work when you're doing a CAPTCHA. With deep learning, you don't necessarily have to label the data, you just shove it through the model and let the model find similarities and differences and categorize and classify things. And so imagine that you have a deep learning, and part of it is called deep because you can kind of see from left to right these vertical rows of neurons. Those are layers. And so we now are using networks that have hundreds or even thousands of layers and millions of neurons. So these are very simple, but a deep learning network would be a model that has many layers. And an example of a deep learning capability would be you feed 1 million news articles in, and it starts to pick up patterns from that data, like news articles are looking this way, and an entertainment article might look like this, and a letter to the editor looks like this. And so we're able to not only do much more powerful work with a deep learning model, but also lower the cost of building it because we don't have to invest in labeling all of the data to tell it what to do. I said 10 years ago there was a big change, and that was to go from traditional machine learning to deep learning. And so there's a couple of examples of that to illustrate that change. One in the upper right here, this is a graph, and it starts in 2010 and goes out to 2015. Every year at this computer vision conference, they would measure the best software, the best AI programs. They weren't necessarily neural networks before 2010. The best ones, and you could see in 2010 that the error rate, which is on the left, is about 28%, which means that you give it 10 images and it gets maybe 7 of them correct and 3 of them wrong if you say, is there a cat in this image or what have you. And then from 2011 to 2012, that dropped from 26% down to 17, and then the next year down to 12, and the next year down below 10, and then by 2015, they were able to go from 30% error rate down to 5%, which is on par with humans. And the reason that they were able to do that was that deep learning, these larger complex networks, were way more powerful at picking out objects and images than their predecessors. And in fact, early in that process, the computer vision experts would look at the deep learning guys and go, you're not really doing vision, you're doing neural networks. And so they didn't really get that this is a tool that they could use until they saw the results here. And then in 2019, Google had started several years before a company called DeepMind, and they did a very large AI network called AlphaFold that was able to take the specification, the DNA specification for a protein, and figure out how does that, what is the shape of that protein when it folds itself up, because proteins are folded up and they're these crazy looking bundles like you see in that picture there. That process at the time, let's say go back 10 years, that process was about 30 days of multiple people working in the laboratory to do experiments and then figure out an approximate prediction for what a protein would look like given a certain specification. And AlphaFold was able to take that 30 days in the lab of multiple people, so the cost of the lab, cost of the people, and reduce it to a few minutes. So with that kind of a change, you can only imagine what this is doing with respect to drug design or treatment design for people. So this is one of the exciting areas of AI, is that it really does have the potential to completely change the game in certain areas. So how does a computer program learn? How many people remember this formula here from, maybe I shouldn't ask you to raise your hand. So I'm not going to ask you to raise your hand. The formula for a straight line on a two-dimensional graph like this is a equals xy plus b, or so y equals ax plus b. So y is the vertical, and in this case, y is a home price. And I want to predict that home price based on the square meters, the space that a house has, and that's my x-axis. And that line, that red line, is an attempt to draw a line through those that would say, even though I don't know what I should price a house that's 325 square meters, I know from this line that it's probably, you can trace the line up from this one that's 300 meters. So I can give that sort of prediction, and that is what these models do, they predict. Well, we can have a program that just guesses those numbers, and maybe it doesn't even get as close as this, and then after it guesses those numbers, we can numerically evaluate how close it came by taking the distance from every one of those points and figuring out the average distance to the line, and then trying to get that, it's a little more advanced mathematics, but basically the average distance between the dots and the line, and we want to minimize that. And so you can have a program that loops through that, and that is at the heart of what these machine learning training a neural network is doing, is learning that formula y equals ax plus b. Only in real life, it's got to do that not just in a two-dimensional graph, but in a multi-dimensional way. So if you think about a house price, this is a screenshot from the house search program called Zillow. The price is going to be affected by lots and lots of things. And so now, not just square footage, but all these values become what in mathematics you would call a vector in that square brackets on the right. And you can take the a equals xy plus, or y equals ax plus b formula and turn it into a much more, sort of hairy, crazy formula at the bottom there, where those thetas, those circles with the zero with the squiggly line through, are now how much does that particular value, x1, which is, we'll say, bathrooms, how much do I influence the house price based on x1, number of bathrooms, versus x2, number of bedrooms? And I might say, well, bathrooms are more important, so then that number gets bigger. So you can kind of see how our intuition, like, well, how do I value a house, can be broken down into these mathematical formulas. And you don't need to know how to do that matrix math, just to know that this then translates into a neural network where those I'll call them weights of how important bathrooms, bedrooms, or lot size is. Those are what are called parameters in a model, which is how much does the green neuron care about each of those different values. And so these neural networks are taking this kind of mathematics and embedding them in software in the form of a network. Now, let's say we have this network, and you can see this network has 5 layers, an input layer, which is the pixels on a screen where I'm going to draw a character, and then 3 what I call hidden layers, and then the output layer is 10 dots because the network is going to guess for each of those numbers that are handwritten what the number is, and if it thinks it's a 0, then the top yellow dot will light up, and if it thinks it's a 9, the bottom light will light up. So we throw these things through. We have the machine learning model guess, just like the line on the graph, and then we compare those things. We say, okay, well, you only got 1 correct, and so we're going to adjust those weights, those parameters, and we're going to try again. We're going to keep doing this until you get 9 out of 10 correct or some maximum number. Now, the way that looks is in the middle here, a 10,000 neuron network, and you'll be able to see the front where you've got a handwritten character, and then as it goes to the side, you can see the layers, and then on the right-hand side, you can see its guess every time. So that's kind of a very simple neural network, and I'm going to go back to the screen here and say, how does this compare? It's about 3 times more neurons than a fly, but 86 billion versus 10,000, way less neurons than a human has. So let's now move from that with character recognition. Now let's talk about what are called language models like ChatGPT. How are these things trained? Well, a model like that, it's going through what's called a pre-training stage, and it's just the first training that it gets with lots and lots of data. And instead of sending one handwritten letter through, we're going to send entire pages of text through. And what we're going to do with that text is we're going to have the model try to guess the next word in a sequence. So we might send it a sentence, and I've got a graph to show you on this. But we'll send a bunch of text through, we'll have it guess, fill in the blank or continue the sentence, and then we'll adjust those parameters as we go. And this is an extremely huge and expensive process, which I'll talk about. But that data will come from the internet, it will come from curated data sources, it'll come from news articles, Wikipedia, et cetera, et cetera. It'll go through the model, and then you'll end up with something that's called a pre-trained model. And in fact, if you think of ChatGPT, the PT in ChatGPT is pre-trained, and G is generative pre-trained model. And generative simply meaning a AI program that can generate text, in this case, generate a poem or what have you. And it took 60 million pages of text going through to train GPT-4, which is compared to about 30,000 pages of text that a person would have read by the time they get their PhD at age 26. These are very back of the envelope numbers, but you can see all the way right away, in some ways, ChatGPT is smarter than your average professor. In some ways, it's dumber than your average 4-year-old. And so it's extremely expensive to train these things. And if you think about the way God created us and the way we are trained, the way our brains are trained, it's pretty amazing how efficient that process is and how we as little kids can start to figure out object permanence and other things. And it's really sort of remarkable. And I keep coming back to this idea that what we're doing with AI is so primitive compared to what God's been able to do with our brains, or for that matter, the brain of a fruit fly. That can like self-preserve mostly and fly around and find food and other things with only 3,000 neurons. We can almost fly a drone with 3,000 neurons, but it's very hard. And it's certainly not a drone that can look for food or avoid a fly swatter. So the way we send those documents through, then you can see we're going to send it a sentence at a time. We're going to blank out words in that sentence, and it's going to try to guess the best probability for that word. And along the way, it builds up this database that associates words with one another in many, many dimensions. And so as it's going through, it says, in the middle of the first one there, would you tell me blank? It takes would you tell me, and then it goes back and decides what's the highest probability next word. And it could be please, or it could be sir, or something else. And so this is how those models get trained. And then once they're trained, you can take a pre-trained model and you can do further training to make it an expert in something like biology or the Bible or geography or medicine for that matter. And that's kind of where lots of action is right now in the science community, is that there are these very, very powerful models that you can download to your laptop and mess around with. I'll show you some examples later. And there are 600,000 just in this site called huggingface.com didn't exist 5 years ago, maybe not even 3 years ago. And already it's this place where people take a pre-trained model, customize it, and then upload it. And you can look at popularity, and there are certain models in certain fields. But 600,000 is a pretty big number there. So what is it? Some scientists in fact, AI scientists they do call these large language models, but they call them token predictors. A token is a word or letter depending on how you design the network. And that's really all they do, is they predict the next token, or for simplicity, the next word. And so if I say, please write me a limerick about Christian professors gathering in Poland, it's like, well, the highest probability first word is certainly. And then it takes all of that, including certainly, and says the next one is here. It takes all of that and does the same thing again. So it's building up a longer and longer context for guessing the next word. And so then I'll just let it finish. I thought it actually did a pretty good job at this limerick, so we'll just let it play out here. In Poland, professors convene with knowledge and faith so keen. They teach and they share in a scholarly air where wisdom and belief are seen. So pretty good, better limerick than most of us could probably write, and certainly quicker. But it was all written because, like at the bottom there, when it decides to do that last word, it's now taking the entire limerick and deciding what's the next word. It didn't think about it ahead of time and write out. It's just like one word at a time, predicting the next token. And so you have to ask, is that model thinking? It's just predicting the next token. And even back in 1980, John Searle was a professor at UC Berkeley, and he proposed what he called the Chinese room experiment. And he said, if I apply it to what's happening with ChatGPT is like this person in a room that doesn't understand how to speak Chinese, but has a rule book and lots of examples of when these characters come in, the best response are these characters here. And so it's constructing a response one character at a time, but it's not constructing that response the way we do. Like if I say, write a limerick, you're going to start thinking about the whole limerick at once, and you're going to do a couple of drafts of it and kind of iterate around. You're not going to do it the way that ChatGPT does. And unfortunately, it won't be as good as ChatGPT, but it's not that ChatGPT is reasoning or thinking. It's that at this scale, the prediction is just really, really good. So there's been, a lot of kind of, I don't know if I'd say a little bit sensationalist comparing GPT-4 or ChatGPT to humans, saying it passed the MCAT or it passed the bar exam. And there are two things that are really important to think about there. So first of all, it might have passed the bar exam because the bar exam and all the answers was part of the training data. And so it better pass the bar exam. It's got perfect memory, and it's an open book test. And another thing and this is one of the reasons it's important for us to know what data was used to train the model, because we can't evaluate the model based on a test that it actually saw as part of its training data. It doesn't tell us anything about the model. And the other thing is, as you've already read, is that just passing, from dealing with doctors, that passing a test to become a doctor does not necessarily make you a good doctor. What makes a good doctor? Judgment, human interaction, and all sorts of other things, the ability to take lots of concepts from medicine and other places. The doctors that are good are the ones that can do way more than what can be measured on a test. Now, large language models are also good at large language or good at language, not so good at math. And so in the, GPT 3.5, which is what came out in November of 22, I guess it was, couldn't multiply two 4-digit numbers. GPT-4 now has a different design where the language model can pull on tools and use tools to get answers. And so now it's going to get that right because it's recognized, I got a math problem, I'm going to use a calculator, I'm going to ask a math model that's been trained on mathematics. But it continues to be a difficult problem of measuring the capability of an AI. And so if somebody says, this AI is as smart as a 12-year-old, you should kind of take that into, a grain of salt with that and ask, well, what tasks of a 12-year-old is it able to do? And it's certainly not all tasks that a 12-year-old could do. So just a couple of examples of that. We want to redesign our kitchen. It's about 4 meters square from wall to wall. And so I thought, hey, I'll just ask ChatGPT for some ideas. I'd kind of like to, go with a larger cooktop, but, what would you say we should do to design? I got this fantastic piece of art, not a very useful design for a kitchen. You could see sort of like some Escher going on here with 2 steps that are going up, but not really going up. And so it still has trouble with the real world. I have some other AI fails later I'll show you. But there are some things that are really, really impressive that AI can do. And if you think about them, they're the things that you could imagine breaking into a computer problem or a mathematics problem. So here's an example. Google came out with a new model called Gemini 1.5. And it was prompted, in other words, remember the limerick, it guessed the last word based on everything before. That's the context of the prompt. And so it was prompted by an entire 45-minute Buster Keaton movie. And then some questions were asked, like a user said, tell me some key information from a piece of paper that's removed from the person's pocket, and tell me the time code of that, when in the movie that happens. And so by training the model, if you will, by including every frame, every still frame of the movie, it could pick out the scene when some man pulls a piece of paper out of its pocket, and it turns out that paper was visible to the camera, and so it could pull that up and say, well, it's a pawn ticket from this particular shop for $4, pawned by Will Smith. Pretty impressive. Even more impressive, the Gemini 1.5 model took user input where the user just sort of sketched a picture on a piece of paper and said, somewhere in the movie this happens, can you tell me where this happens? And it was able to find, by doing a comparison of the sketch with frames in the movie, it was able to find that particular, so this happens at time 15 minutes and 27 seconds into the movie. So pretty darn impressive stuff. Real quickly, what changed 2 years ago? It was supercomputing. Supercomputers got we always are, I've been in the supercomputer business since 1985, and these things increase in their capability. And we finally got to the point, if you look at these graphs, like forget the mathematics and stuff, all of them have this hockey stick characteristic at about 10 to the 22. And that number at the bottom is like the number of instructions that the computer had to go through to train the model. 10 to the 22 instructions. Somehow, in all of these different tasks, word unscramble or what have you, at about 10 to the 22 instructions, or that amount of training, the model got really, really amazingly better at these capabilities. And if you look at the way computing is, and you can sort of see at the bottom what these numbers mean. A laptop, this laptop here, which costs about $100 a year to maintain, it would take this laptop 27 years just to do 10 to the 20th, which is 100 times smaller than what we need to get to that inflection point. It would take a supercomputer like the one you see there 4 years. And a supercomputer is $500 million, roughly speaking, and about $100 million a year. So these are very expensive models to train. And that's why it's really significant that those expensive to train, pre-trained models have been made available so that people can, on a laptop, retrain them or or modify, augment their training with special capabilities. So it means that it sort of democratizes AI to some degree, but there is still some concern that it's so expensive to build a new model. Like, let's say you change the design of the model and then you want to retrain it from scratch. Well, there are only a handful of entities on the planet that can afford to spend $100 million training a model. So supercomputing in the last 2 or 3 years just sort of got to the point where finally we saw this inflection curve happening. I showed you this fruit fly, 3,000 neurons, a person, 86 billion neurons. This is one of about 20 rows of computer equipment that we have at where I work at Argonne National Laboratory. This is, in terms of AI capability, it's the most powerful computer in the world. In terms of general science, it's the number 2, barely beat by number 1, which is at another US research laboratory. If I run on that a 86 billion, 1 trillion parameters or neurons synapse model, I can actually train it on a machine this big in a feasible amount of time, still very expensive. I can run that trillion parameter model once it's trained on a different machine. But now let's think about God as the most amazing engineer you can imagine. Our brain runs on about 20 watts of electricity, which is 4 watts less than 3 electric toothbrushes. So like maybe 5 of these pointers, and our brain runs on that. And 10 years ago, a supercomputer, the fastest in the world, took 5 megawatts, which is enough to light up a World Cup stadium at night. And the machine in that picture there, which we're really proud of, it's like not as smart as me, but we're really proud of it. But it doesn't run on 5 megawatts, it actually needs 60 megawatts. So this is like enough stadium space. These are 12 largest stadiums in Europe. You might recognize your hometown there if you're from Barcelona or Madrid or Munich or Manchester, England. I did throw in the largest one in Poland, the largest one in Romania, but I don't remember which ones they are. So that's enough seating space to light up at night to watch a game for about 700,000 people, the collective. And that's what it takes to run one of these machines. So we're pretty proud of this machine, but we're kind of a far cry from doing that kind of thing on 20 watts. So we have a lot of work to do in the science community to get even close, even in the same ballpark as God's capability for engineering.